All right, let's dive straight into this explainer. We all know AI agents look incredibly cool in demos, but today we're talking about reality. We're looking past the pristine local environments and talking developer to developer about what actually happens in production. Because here's the central thesis. To build truly trustworthy AI agents, we don't need more magic prompts. We need boring, battle-tested distributed systems patterns.
So to understand why, we need to draw a hard line in our architecture. On one side, you've got the LLM. Think of this as your probabilistic brain. It's smart, it reasons, it interprets intent beautifully, but it's fundamentally just guessing the next most likely token, right? It is not exact. On the other side, we have your application code, the deterministic muscles. This code does exactly what you tell it to do every single time. So the absolute key to building reliable agents is separating that fluid reasoning of the model from the strict deterministic execution of your code.
It's so easy to forget this when you're just prototyping. I mean, in a flawless localhost demo, everything flows so beautifully. The prompt comes in, the LLM makes a tool call, the local API responds with a success message, and boom, you get a happy little green check mark. It literally feels like the future. But as we all know, localhost is a lie.
Let's move to production and see how this setup turns into an absolute disaster. Say you've deployed an AI financial assistant. A user types a super simple command, pay the $500 Acme invoice. The intent is crystal clear and the probabilistic brain understands it perfectly.
The agent dutifully goes to work. It validates the invoice, formats the API call, and submits the payment to your external provider. The provider gets the request, everything checks out, and they successfully process the $500.
But here is where reality bites. Right as the provider sends back the success confirmation, there's a network blip. A router somewhere drops a packet, and the acknowledgement just vanishes into the ether. Suddenly, our poor application and the agent are left completely in the dark, staring at one terrifying word, timeout.
Now, if you've given this agent basic autonomy without strict guardrails, it's going to use that probabilistic brain to fix the problem. It thinks, well, the tool call timed out, guess it didn't work, I'm a helpful agent, I'll just retry. So it fires off the exact same tool call. This time, the network is perfectly fine, the second payment goes through. And just like that, Acme just walked away with double the money. You just paid $1,000 for a $500 invoice. Yikes.
What's really painful about this is the irony of it all. Every single individual component behaved completely reasonably, yet the overall product totally failed. The agent did what it was supposed to do. It tried to fulfill a prompt by retrying what it thought was a failed step. The payment provider did what it was supposed to do. It processed a valid request. So why did it fail? Because at the end of the day, production AI agents eventually just become distributed systems problems.
To cage this chaos, we have to introduce our first incredibly boring developer control. We absolutely must establish a hard boundary between a network retry and a completely new business action. This boils down to the difference between request identity, which just means a network packet was sent, and business operation identity, which is the actual real-world intent, like paying that specific invoice.
And we solve this using a deterministic operation ID, something you probably know as an idempotency key. Think of an ID like 7F4E-91BA-22AC. Here is the golden rule. The LLM should never just hallucinate a new operation ID on every single retry. Because it's a probabilistic engine, it might tweak a single character, and suddenly that retry looks like a brand new payment. This ID belongs strictly to the boring deterministic application state. You generate it once in your code, and you force the agent to use it.
This perfectly illustrates a foundational concept in distributed systems. Message count does not equal business action count. Just because a message gets sent over the network twice, or even 10 times because of lag or timeouts, does not mean we should actually charge a credit card multiple times.
Which brings us right to idempotency. It simply answers the question, what happens if the command runs twice? In a well-designed system, if a retry uses that exact same operation ID we just talked about, the receiving system recognizes it. It goes, I already processed 7F4E. I'm going to safely do nothing and just hand you back the original success message. Problem solved.
All right, next up, explicit state machines and keeping agents on track.
So, idempotency protects us at the API boundary, but we also need to protect the agent from itself. This is our second layer of defense. You really can't just give an agent a massive list of tools and pray it picks the right sequence. Instead, you have to build a track by defining strict, linear steps like invoice received to validated to pending to submitted to completed
we intentionally limit the agent's autonomy. The agent doesn't get to decide the whole workflow. It is only allowed to transition the system through legal, predefined checkpoints. The deterministic muscles define the track, and the LLM brain just pushes the cart.
This dynamically restricts what the agent can even attempt to do. If our state machine currently sits at payment submitted, the next action we give the agent should never be to pay again. That tool should literally be yanked from its context entirely. The only legal tool available at that point must be to verify the existing payment.
Which actually brings us right back to our original disaster scenario. We hit a timeout. But let's pause. What happens when reality stops answering? Does a timeout automatically mean a failure? As we saw earlier, absolutely not.
A timeout literally just tells us that communication broke. It tells us zero about the actual real-world state. That business operation might have completely failed, or it might have actually succeeded. That means a timeout puts us in a very specific, critical state, unknown. And from unknown, you don't just blindly retry. You have to verify, reconcile, and only retry if it is cryptographically safe to do so.
So how do we handle that uncertainty? With reconciliation. After hitting an unknown state, reconciliation is how we compare our local state with external reality. We take that original deterministic operation ID and we explicitly query the payment provider. We're basically asking, hey, did you ever actually see an operation with this specific ID?
Based on what the provider says, our state machine can move forward safely. If they say success, awesome, we update our local state to confirmed. Crisis averted. If they say failed, we know we can safely trigger a retry. And if we still can't determine the result, like maybe their whole API is down, the system should gently hold the process or escalate it to a human. A system should always gracefully degrade rather than wildly guessing with someone's money.
Let's bring this all together. These 3 boring developer controls are literally the secret sauce to making your shiny new AI agent trustworthy. Idempotency answers. What happens if the command runs twice? State machines answer. Is this action even legal right now? And reconciliation answers. Does our internal state actually match reality?
This leads us to a beautiful architectural pattern called the asymmetric control loop. It's the perfect handoff. The LLM acts as the reasoning layer. It processes intent and proposes a plan, but it operates asynchronously, handing its intent down to the deterministic controller. That controller manages the how within hard, unyielding safety bounds. If the LLM proposes an action outside that safety envelope, the deterministic layer simply rejects it.
For us as developers, this requires a big shift in how we view these models. The LLM is really just another API. It's a component, not the whole system. Your surrounding application code has to take full ownership of identity, state management, retry semantics, legal transitions, recovery, and auditability. Please do not outsource your system's reliability to a prompt.
Now, don't get me wrong here. It is incredibly fun to watch that probabilistic brain at work. The exciting part of building with AI is watching the model interpret nuanced intent, break down complex goals, and intelligently propose actions. It truly feels like magic.
But as you build for production, I want you to remember this. The expensive part is what happens when reality stops answering. The model can propose the action, sure, but your system, not the model, has to be the muscular safety net that catches the pieces when the network drops, APIs fail, and things go wrong. So I'll leave you with this to chew on. Is your current AI agent relying on the magic of a model to stay safe, or is it firmly grounded in the boring, bulletproof patterns of distributed systems?